Assalamu alaikum wa rahmatullah. Hi dear students, I'm very lucky to be back with you with another video lesson. And I hope you've been practicing very well lately. In the previous lesson, we were talking about Newton's second law of rotational motion, which the torque or net torque was equal to moment of inertia multiplied by the angular acceleration. And of course, today we'll talk about a new concept, which is angular momentum. Now, what is angular momentum? You have an idea about momentum, which you've studied in, let's say in grade 11, yes? But in grade 11, we said, for example, whenever there is an object that has a mass, for example, and if it is moving, let's say, in a straight line, of course, we were saying the momentum of this object would be mass times velocity, okay? So this would be the momentum of an object that is moving in a straight line, or momentum in translational speed, let's say. And of course, this was a vector quantity. It could be right, it could be to the right, which was positive, to the left would be negative. This year, we do have the same concept, which, but the concept will be a little bit different because we're talking about rotation here. So instead of saying momentum here, of course, we will say angular momentum. And of course, we use capital letter L for that. And of course, we do know that instead of mass, of course, we're going to use what? We're going to use moment of inertia, and then multiplied by, instead of speed, we're going to use angular speed. So we can say that the angular momentum is the product of what? Of moment of inertia, and of course multiplied by the angular speed. Okay, so far you've learned that we have some linear and angular quantities. As we said, of course, delta x equal to delta x, starting with delta x, let's say, was equal to, let's say, angular displacement. And of course, we said velocity or speed equal to angular speed in this case. And acceleration, of course, it was angular acceleration, let's say. And then these are not equal. This like linear quantities, these are rotational quantities. And of course, after that, we talked about force, and force was, let's say, in rotational motion would be the torque or the net torque. And of course, some other things that we have. And then what else did we have? We talked about mass, and of course, mass in rotational motion would be the moment of inertia. Okay, and then of course we have later on, you will see that. So let's talk about momentum as well. So momentum, now we have angular momentum, and then later on you will see that we have, let's say, kinetic energy in translational motion, and of course we will have kinetic or rotational kinetic energy in rotational motion as well. And of course there is more, but these are the quantities in linear and rotational motion that I want you to remember for now. So let's talk about angular momentum one more time. So we can say angular momentum is the product of moment of inertia. That would be the analogies of mass, and of course multiplied by the angular speed here. What about the unit and direction? Is angular, by the way, momentum was a vector. So what about the angular momentum? That is also a vector. Here we're going to use the right-hand rule, but it is not our concern for this year or in this level. So we're not going to talk about the direction much. Rather, we just talk about the magnitude of the angular momentum. So what about the unit? We know that the unit of angular moment, the moment of inertia, what was the unit for that? The unit was kilogram meter squared. Yeah. What about the unit of angular speed? And of course, angular speed was radian per second, but we said radian was a dimensionless, yeah? So we can just say 1/second, or you can rewrite this one. You can say the unit of angular momentum would be kilogram meter squared over second. And of course, this is one. We do have another unit for angular momentum, which you will see that, of course, we will use joule second as well. Keep in mind, once we get to this, or where we get this unit, of course, I'll inform you about this unit as well. So very simple, very easy. Okay, so angular momentum, the moment of inertia multiplied by the angular speed, and that's all you need to know for now. By the way, so here's the definition, here's the equation. You can see the units in which what are each letter standing for. Now, the analog, or the analog, you can say, of linear momentum in translational motion is the angular momentum. We've talked about this. By the way, angular momentum is a vector quantity and has the same direction as the angular speed. And of course, we can use or measure that using the right hand rule. Okay, so you've studied this in grade 11 in translational motion. We have momentum, which is equal to mass times velocity. And then in rotational motion, of course, the angular momentum. So this is just momentum. L stands for angular momentum. And of course, moment of inertia multiplied by the angular speed. Take a look in this equation. We can say the angular momentum is directly proportional with what? Is directly proportional with the moment or the inertia. Okay? So moment or angular momentum is directly proportional. So here's the equation. Take a look here. So by increasing I, of course, L will increase as well. What about by increasing the angular speed? L or angular momentum will also increase. But if you rearrange the equation, what will be the relationship between the relationship between angular speed and moment of inertia? So you can see here these two are directly proportional, but if we rearrange the equation, moment of inertia would equal to L or angular momentum divided by angular speed in here. So, which means that, okay, by increasing the angular momentum, of course, the moment of inertia would increase. And if we keep this one constant, all right, then of course, by increasing the angular speed, moment of inertia would decrease, because you can see that these two are inversely proportional. And of course, by lowering the angular speed, moment of inertia will also increase, okay? Or will increase in general. So you can see the relationship between the two is inversely proportional. Okay, now we have the law. Previously, we had the law of conservation of momentum, yes? So basically, we said momentum before the interaction or before collision is equal to momentum after or equal to the momentum after the collision. Let's say momentum before and after the collision were the same. Or we could have said, for example, momentum before the interaction is the same or equal to momentum after the interaction. Here, we can say the law of conservation of angular momentum. Can the angular momentum be conserved? Yes, in one condition. So we can say the law of conservation of angular momentum is when the net external torque acting on the object is zero. So you might be asked, when will the angular momentum be conserved? So your response should be this: the angular momentum will be conserved if the net torque acting on the object is zero, okay? So if not, then of course it will not be zero. So by the way, sometimes we have more than one object, so you can say if the net torque acting on the object or objects is zero, okay? So we can say the angular momentum of that object or the objects in general will be conserved. So what do we do when the angular momentum is conserved? We can say this, all right? So we've learned that angular momentum equal to what? Equal to moment of inertia multiplied by angular speed, yes? But if we're talking about the conservation law of angular momentum, we can say, by the way, so we have angular momentum before and after, yes? So we can say initial angular momentum will equal to the final angular momentum, yes? But what is initial equal to? We can say I, that would be, let's say initial moment of inertia multiplied by initial angular speed will equal to I times omega, but these are final. So we can say initial moment of inertia multiplied by the initial angular speed is equal to the final moment of inertia multiplied by the final angular speed. But remember, when do we use this? We will use this if we have one object, okay? What will we do if we have more than one object? In this case, of course, we will say the initial angular momentum of object 1. Let's write it down. Okay, so in this case, once again, initial and final will be equal, but in this case, we'll say the moment of inertia for the initial for the first object, okay, plus the initial for the second object will equal to the final for the first object plus final for the second object, yes? But now, what are each one of these equal to? And of course, you know this. This is going to be each angular momentum equal to what? Moment of inertia, right? So this would be initial. These are for the first object, plus, once again, moment of inertia, multiplied by the angular speed. These are initial, by the way, but this time is going to be for object 2. So we have initial for object 1, initial for object 2 will equal to moment of inertia, final for object 1, angular speed of final for object still number 1, okay, plus, of course, we're going to write the same thing, but for the second object, yeah? Remember, this time, we have the final moment or angular momentum, okay, for object 1, and then plus the final angular momentum for object 2. All right, so in this case, it's going to be I omega. These are final for object 2 and object 2. So this is what we have. But by the way, most of the cases here, this 2 would be equal here. So we can say I initial 1 plus I initial number 2, where the second object multiplied by the initial angular speed will equal to I final for object number 1, you can say, plus I final for object number 2 multiplied by omega final. So because the objects would be, like moving together, so they would be having the same angular speed, initial, or their initial angular speed would be the same, and of course their final angular speed would also be the same. So most of the time in questions they will ask you to find final angular speed of the object. So how are you going to find final angular speed in here? Yes, can we divide both sides by moment of inertia, let's say final for object number 1 and 2? Yes, so or we can just say move this part under this, and of course you will find the final angular speed. So let's move this up a little. So we can say omega final, so and this would be, this is, what you will be required to solve, to find in most of the questions that you will see. In this case, of course, you will say I initial for object 1 plus I initial for object 2, that is initial, right, initial what? Angular speed divided by moment of inertia final of object 1 plus moment of inertia, let's say final of object 2, and this is what you're going to use, of course, to find the final angular speed. But let me tell you something, yeah? When do we have, let's say, two different moment of inertia for an object? All right, so let me tell you. When we have an object, let's say, an object is on a merry-go, let's say, yes? Now this merry-go would be rotating, of course, so if it is rotating, it would have a certain moment of inertia, yes? And of course, we can think of this as a solid disk, you can say, or just as a disk. So moment of inertia in this case is going to be 1/2 m times radius squared. That is the moment of inertia for the disk, or for the merry-go in this case. So it has a certain radius, okay? The radius of the merry-go doesn't change. So what if we have, let's say, a child that is at the beginning, he or she is sitting very close to the center of the merry-go. And remember, because it is a child, when we consider the child to be, to act or to behave, or consider as a point mass, so the moment of inertia of the child is going to be m times radius squared, yes? But later on, okay, this child will be moving outward, so the child will come to a point that is here, let's say. So the radius is 0.5 here, and then the radius here is going to be 1.5. So you see, the radius is going to change for the child. If the radius is going to change, do you think the child will have the same moment of inertia later on? Of course not. Why? Because the radius is going to change. So remember this, if something's radius is going to change, the moment of inertia will always be the same. In another word, the initial and final moment of inertia for that object will always be the same. But for the person that is being rotated, for example, as a child, it is on a disc, on a merry-go-round, so it is being rotated, yeah? As long as the radius of the child or any other objects that the radius can change for them, they will have two moment of inertia. So you can consider the first one to be moment of inertia of 1, all right? And then second moment of inertia will be again mass times the radius squared. But because the radius changed, so that means moment of inertia of 1 will not be equal to moment of inertia of 2, or the second time. And we already know that. Keeping the moment or the angular momentum the same by increasing or decreasing the moment of inertia, of course, the angular speed will be affected, because remember, we said angular momentum equal to what? Equal to moment of inertia multiplied by the angular speed. So this one, if this one is conserved, if there's no external torque, if there's no external force acting on the merry-go-round, that means by increasing this, what will happen to this? This will decrease. What if you do the opposite? What if you decrease I, moment of inertia? Of course, the omega will increase. So remember, any change to the moment of inertia will affect the angular speed if the angular momentum is kept constant or conserved. Okay, so let's see and solve a few questions here. All right, so here are the equations. That is, moment of angular momentum, initial and final, would be equal, assuming there's no net force on the object, or the net force is 0. Okay, if it is more than one object, here's what we use. So remember, try to highlight this, or make sure you write this one down, because this is the equation that we're going to use for most of the cases, yeah? Whenever they are asking us to find the final angular speed for the object. Once again, because any change in the radius of the person, that would change the moment of inertia for that person, for that object, and then of course that would affect the angular speed of the whole system. Okay, so keep this in mind, write it down and highlight it. And of course we can say this too, because the relationship between these are inversely proportional. By increasing or decreasing angular speed, the moment of inertia will change. Now, how do we apply the law of conservation of momentum for an ice skater? Okay, you've seen ice skaters, you know, like once they are, let's say, when they are spinning on the ice, yeah? Normally, what do they do, for example? If they are extending their arms, remember, the mass would be far, or will be far from the center of their body, center of their mass, let's say, and we know that as the further the mass, what will happen to the moment of inertia? Will it increase or decrease? It will decrease? Yes. No, actually, it's the opposite, yeah? So remember this, the further the mass from the axis of rotation, the bigger the moment of inertia. If the moment of inertia is big, so what do you think will happen to the angular speed? By keeping the moment or the angular momentum constant. So remember, L equal to what? I times angular speed. So once we are extending our arm, right, what will happen to I? Remember, let me get a rectangle and then tell you exactly how this works. Okay, so what happens when the angular momentum is kept constant? So we know that angular momentum equal to what? Equal to, we said it, moment of inertia multiplied by what? By the angular speed. Excellent. So what happens when we extend our arms? Yes. So normally moment of inertia, let's say for a person or for objects, let's say for a person, if we consider them to be a point mass, so that is going to be, let's say, 1/2. Okay. Actually, let's just say mass times the radius squared. Yeah. All right. So what happens? Okay. What happens when we extend the mass, or let's say add or put the mass far from the center of rotation? Once we extend our arms, this R will increase. Do you agree with me? Excellent. So what happens if R increases? Can we say that the moment of inertia will also increase? Yes. By keeping this constant, if you increase this one, if you increase the moment of inertia, okay, what do you think will happen to the angular speed? Of course, this one is going to decrease. So this is the reason why when the ice skaters extending their arms and maybe one of the feet as well, so their spinning or their rotation will slow down. Why? Because moment of inertia gets bigger, so the angular speed gets smaller. But what happens when they bring their hands closer to their body, closer to the center of rotation, or closer to their chest, let's say, and of course their feet as well? So of course in this case, R will be what? R In the second case, r will be reduced. Yeah, if r is reduced, moment of inertia will be reduced, or it will be smaller. Very good. And guess what happens when I get smaller? If I get smaller, so keeping the angular momentum the same, so I multiply by angular speed. So if I is reduced, and of course the angular speed will increase. So this is the reason why once the ice skater bringing their hands closer to their body or to the center of the rotation within their feet, of course, including their feet, this will make them spin faster. So remember this. Make sure you write some notes. By extending the arm, I increases because radius increases. The mass is further or far from the axis of rotation. All right, we said by keeping L constant, if I increase, L decreases. All right, and of course we have the law of conservation of angular momentum here. So what happens when we bring the hands closer? I decreases. If I decreases by keeping L constant, omega angular speed must increase, and of course that is the law of conservation of momentum or angular momentum. Very, very good. So here we have a question. It says, what happens when an ice skater brings his hands and feet closer to his body? Of course, very good question, yeah? We said it earlier. So once we bring our hands closer, the R, all right, or the mass that was far from the axis of rotation will be closer. If it gets closer, R will be less. If R is less, that means the moment of inertia will be less. So this will make the angular speed to be higher or faster or just bigger in this case, okay? By keeping the moment of, or the angular momentum constant. So the moment of inertia decreases, his angular speed increases. Now take a look at question 24 in chapter review. It says, is the angular momentum always conserved? And that is a very good question. Can we say the angular momentum is always conserved? The answer, explain your answer. All right, so let's explain this. So tell me, what do you think about this, yeah? So we said there's only one condition for the angular momentum to be conserved. What was that one? Did you highlight? Do you recall the reason? Yes, very, very good. So the angular momentum will be conserved only if the net force acting, or the net torque in this case acting on the object, is 0, okay? So we can say converted only when the net torque acting on the object is 0. Now we have another question. Question 25 says, is it possible for two objects with the same mass and the same rotational speed to have different values of angular momentum? That is a very good question as well. So we have two objects, and the two objects have what? Have different, it says with the same mass, with the same mass and same rotational speed. Is it possible for them to have a different value of angular momentum? Very good question. So take a look here. So we have two masses. So angular momentum equal to what? Equal to moment of inertia multiplied by angular speed. So we have two objects, and the two objects have the same what? The same mass and the same angular speed. All right? When these two objects have different mass and angular speed, is it possible or for them to have a different angular momentum? The answer is yes. And why? Because angular momentum depends on what? Depends on moment of inertia. And moment of inertia depends on what? Depends on the shape of the object, because there is a factor that we have that we multiplied by mass times the radius squared, and then multiplied by angular speed, yes? So it is possible for two objects that have the same mass and the same angular speed, yeah? But remember, if they don't have the same radius, because there is a radius in the equation, yes, it could lead to a different moment of inertia. If they don't have the same shape, all right, because it could be, this factor here could be 1, could be 1 over 2, could be, let's say 5 or 2 over 5, yes? Could be 2 over 5, or could be, let's say 2 over 3, yes? Or could be 1 over 12, or whatever it is, yeah? So depends on the radius of the object, depends on the shape of the object as well. So yes, it is very possible for two objects, even with the same speed and mass, but with a different angular momentum. And the reason why? Because the angular momentum depends on the moment of inertia, not just the mass, yeah? So when can we have, or when will two objects will have the same angular momentum? In this case, if you want to know when, then you got to pay attention carefully. Two objects with, let's say, two objects will have the same angular momentum if they have the same angular speed, if they have the same mass, if they have the same radius, and also the same shape as well, because even the shape could determine, or there could make a difference in the angular momentum as well. So two objects will have the same angular momentum if each one of these values were equal. All right. And of course, there is another. By the way, there could be a different way as well. For example, we could have a different, let's say, angular speed, but maybe the mass will compensate for that. Yeah. Let's say if this one is half, let's say the angular speed is half. Let's just say. And then if the mass is twice as that, of course, these two will cancel each other out, then you would get the same answer as well. So it is possible for these values to change, yeah, but eventually all the result of the angular momentum must be equal. Then, of course, we'll have the same angular momentum. So you can take a look here. This is the explanation of what I've just explained. Now we have another question. Question 26 says, a child on a merry-go-round moves from near the axis to the outer edge of the merry-go-round. What happens to the rotational speed of the merry-go-round? All right, so once again, we have a child, okay? So here's the merry-go-round, okay? So let's say here we are, okay? The child is very close. Let's say here's the child. Is very close to the axis of rotation. So what happens when the child goes further? I hope I didn't say the opposite. So what happens to the rotational speed near the axis? Yes, and then to the outer edge. So going back to this. All right. So here's the child, which is very close to the axis of rotation. What happens to the moment of inertia, all right, or to the angular speed then when the child goes, for example, to the outer edge of the merry-go-round? So once again, okay, we have angular momentum. We're considering that the angular momentum is conserved. Okay, so angular momentum equal to moment of inertia multiplied by the angular speed. So what happened to the moment of inertia as the child moves closer to the edge of the merry-go-round? The radius, let's call this one R1 and R2. R2 will be bigger, correct? So if we consider this as a disk, 1 over 2 mr squared, yeah? So r squared, or r, the radius will increase. If r is increasing, what do you think will happen to the moment of inertia? Excellent. So moment of inertia will increase. If moment of inertia is increasing, and this one is constant, this one doesn't change, so what do you think will happen to the angular speed? Of course, it must decrease, and that is the correct answer. What if it was the opposite? What if the child was at the edge, and then, or closer to the rim of this, and then the child started to move closer and closer towards the center of the merry-go-round? In this case, r will reduce. That means moment of inertia will reduce, and of course, angular speed will increase. All right, moving on. By the way, says the angular speed decreases because the moment of inertia increases. We've just talked about this. So, and of course, remember r, why? Here's the reason why, because r gets larger, moment of inertia gets larger, so omega, or angular speed, gets smaller, keeping L constant. So we have another question, says 27. Is it possible for an ice skater to change his rotational speed without any external force or torque in this case? And I'll explain your answer. It is yes, absolutely, yeah. So remember that if the arm of the ice skater are extended, that means we have a large R. If R is large, that means moment of inertia is large, angular speed is low. Yes. What happens if let's say she or he brings the arms closer to the center of the body or to the center of the rotation, then of course moment of inertia reduces, angular speed increases, so they will spin faster even without any net or net torque, we can say. All right, now we have two study tips, and these are very important. I want you to pay close attention here. It says objects that are rotating, or that is the object that is rotating basically, whether if it is a merry-go, a cylinder, a disc, a ring, has one moment of inertia. When do we use this? We use this one for the law of conservation of momentum, because we have initial and final, yeah? So if we have an object that has a solid shape, all right, if the shape doesn't change, if the radius doesn't change, that means initial and final moment of inertia will be the same, because this radius will never change. Yes, it is a solid object, of course, so what do you expect? So as long as the radius doesn't change, that means your moment of inertia is always the same. Initial and final will be the same, whether if it is merry-go, cylinder, disc, ring, or whatever. That's one, yes? And of course it doesn't, so because the shape doesn't change, it has a fixed radius. Now, I hope you understood this well. What about the object or the moment of inertia of the object that is being rotated? Let's say there is a child on a merry-go. There is an object on a, let's say, on a disc, let's say, that is being rotated. So whatever the object that is being rotated, if the radius of the object is going to change, we'll have a different moment of inertia. A different moment of inertia would lead to a different angular momentum. Excellent. So the moment of inertia for an object being rotated, whether if it is on the merry-go, cylinder, disc, or a ring, will vary if it is a distance from the center of rotation is changed. So we will have different r's, radius 1 and radius 2. Okay? As described by the equation m multiplied by the r squared. Why are we using mass times the radius squared? Because we consider this person, for example, to be as a point mass, let's say, or as a thin hoop, yeah? Okay. Was it a hoop? Yes, I think it was. Now, take a look at this sample problem. It is very important for you to pay close attention, because understanding one example would save you a lot of time, and I can tell you that most of the other questions would be very similar to this. So let's see how well you can get this. So we have a 65 student which is spinning on a merry-go-round, okay, that has a massive 5.25 times 10 to the power 2 kilograms. So we have mass of the student, mass of the merry-go. What is the radius of the merry-go? It is 2 meters, as you can see here. So we have the merry-go-round, yes, and then the mass of the merry-go, the radius of the merry-go, and then she walks, that is the child, okay? She walks from the edge of the merry-go. What does the edge of the merry-go mean? That means the first radius for the child will be the same as the radius of the merry-go, which is 2 meters. Excellent. If the angular speed of the merry-go is initially 0.20 radian per second, what is it is angular speed when the student reaches a point of 0.5 meters from the center? Now this is very important. I want you to pay attention here. I'll do it in two different ways. I'll do the first way, then of course I'll do an easy way, which is just one step, and you plug in the numbers, you get the result. So let's do this together. First we'll do it the hard way, see how well you understand it, and then of course we'll move forward. All right, let's get this one back. Okay, so take a look once again, write all the information that is given. So we have the mass of the child, which is, let's say C for child, 65 kilograms. Okay, and then we have the mass of the merry-go, which is 5.25 times 10 to the power 2, that is kilogram. The radius of the merry-go is 2 meters, okay? And by the way, the radius of the child, or how far the child is, it says she starts walking from the edge, yeah? That means the radius for the child will also be 2 meters. Don't forget this. Okay, and then what else do we have? If the angular speed of the merry-go initially, so we have angular speed or initial angular speed of the merry-go, which is 0.20 20 radian per second. Okay, and then what is the angular speed when she or the student reaches a point of 0.5? So we can say radius 2 for the child will be 0.5, okay, from the center of rotation. What is the omega final angular speed? All right, take a look. Because we're talking about angular momentum here, so we can start with this. Initial angular momentum equal to final angular momentum, yes? But do we have one object or two? So two, don't forget. So we can say initial angular momentum for first object plus initial for the second object. The first object here in this case is the child or the student, and this would be for the merry-go. Let me write child and merry-go or student here for the child, and then merry-go here. That is initial as well, equal to, once again, that is going to be final plus final. One of them is for the student and the other one is for the merry-go. But take a look here. What is the angular momentum for each one of these? We can say the angular momentum for the student is going to be mr squared. Yes. All right. That is for the student, and then plus. What about for the merry-go? For the merry-go, of course, it is like a disk here in this case, so it's going to be 1/2. I forgot the. Let me write the angular speed as well. So multiplied by angular speed of the first or of the student plus, let's move this one a little bit far. Oh, not this. Let's see, I think we won't be able to move this. Okay, anyway, so just remember, we'll just continue this way. So the angular momentum for the merry-go is going to be I times omega, yeah? I, that is going to be 1/2 mass times radius squared, and then we can say omega initial for the merry-go equals to, now, omega final angular momentum for both, of course, for the child and for the merry-go. So, of course, for the child is going to be m, we can call this one r1, by the way, right? Because the radius for the child is changing. So mr squared multiplied by omega final, that is for the student again, plus once again for the merry-go, it is 1/2 mr squared multiplied by omega final. This is for the merry-go. But take a look here, there's one thing I want you to know, because the child and the merry-go are moving together, yes? So can I say they both have the same angular momentum? Not the same angular momentum, the same angular speed. Because the child is being rotated on the merry-go. So in this case, both the child and the merry-go are moving with the same angular speed in here. So we can say, of course, I should have done I first so that you'll be less confused here. So we can just say, let me just write this one here. I for the student, right, plus I for the merry-go, which you can see the equations, initial, all right? That'll be the same initial. What about the final? Of course, even their final angular speed will be the same as well. So I can say I for the student, which is final. These are initial, by the way, initial, right? For the student plus I final for the merry-go multiplied by final angular speed as well. So this one is what we're trying to find here. So omega final equal to what? What is omega final equal to? So omega final will equal to initial, or just this, right, over the this one here, because we can move this one under this side where we can find the answer there. So we can say I initial for the student plus I initial for the merry-go multiplied by the initial angular speed, right, divided by moment of inertia for the student, final, that'll be the second one, for the student plus final moment of inertia for the merry-go, and then of course you plug in the number, that'll be the final angular speed. You plug in the number, not the number first, you'll have to find their moment of inertia, then of course you can find this one here. Okay, so I think it is taking long here. It was supposed to be faster than this, but here's the equation, yes? Now, all you need to do is find the angular or moment of inertia for the student, moment of inertia for the merry-go, and then second moment of inertia for the student because the radius is changing. And then second moment of inertia for the merry-go would be the same as first. Why? Because the radius of the merry-go doesn't change. So let's erase some parts and then plug in the numbers and solve this together. So let me erase this. Let's find the moment of inertia for both the student and the merry-go. So let's say moment of inertia for the student, initial by the way, for the student. We consider the student, for example, as a point mass or as a, let's say, thin hoop. So in this case, we'll use mr, yeah? But remember, this is radius, the first one, okay? So in this case, the mass of the student, it is 65 kilograms multiplied by the radius is what? The radius, she walks from the edge of the merry-go. Edge of the merry-go has a radius of 2, so in this case it's going to be 2, but it is squared, yeah? So 65 times 4, what is the answer? 65 multiplied by 4, that is going to be 260, yes? And kilogram meter squared. That is the initial moment of inertia for the student. Okay, what about the final? Why the final? Because the radius, she's going to walk closer to the center, yeah? So in this case, the radius will change, that means the moment of inertia will change. So once again, mass times r2 this time squared equal to 65 multiplied by the radius this time, it is just 0.5. Don't forget the square. So 65 multiplied by 0.5 squared, the answer will be 16.3. 16.3. So take a look. What happens to the moment of inertia? Okay. Once the person gets closer to the axis of rotation, moment of inertia reduces. So the angular speed must increase. Now that is for the student. What about for the merry-go? Because the radius of the merry-go doesn't change, so we can say moment of inertia for the merry-go initial equal to the final moment of inertia for the merry-go, right? Which is equal to merry-go is like a disk, right? So in this case, 1 over 2 mr squared. So once again, 1 over 2. The mass of the merry-go is what is it? It is 5.25 times 10 to the power 2. 5.25 times 10 to the power 2 kilogram multiplied by the radius. What is the radius? It is 2, but 2 squared, don't forget. So calculate all this. 1 over 2, that is 0.5 multiplied by 5.25 multiplied by 10 to the power 2. Ten to the power, where am I? Okay. 10 to the power 2. Okay, and multiplied by the radius squared, which is 2 squared in this case. 5.25 times 10 to the power 2 times 2 squared. So the answer is, we can say 1050 or 1050, yeah? So 1050. And of course that is kilogram meter squared. Okay, so remember this. This is for the merry-go, both the initial and final moment of inertia will be the same. The reason why? Because the radius of the merry-go doesn't change. So it is the same. Now all you have to do is just plug in the numbers here, and of course you will find the answer. So let's plug in the numbers here. Let's erase this part as well. I don't want to erase the whole thing. So let's use a different color. So in this case, let's write it here up here. So omega final, or final angular speed here, is going to be the initial moment of inertia for the student. It was what? It was 260. So 260 plus the final moment of, or initial moment of inertia of the merry-go, which was 1050, multiplied by the initial angular speed. What was the initial angular speed? It was 0.20 or 0.2. So multiplied by 0.20. Okay, and then divided by final moment of inertia of the student. What was final? It is 16.3 plus the final moment of inertia of the merry-go. We said final and initial for the merry-go is the same, so 1050. And then divide all this, and then you will get the answer. So let's do it together. We can use a bracket. That is 260 plus 1050 multiplied by 0.20 divided by, you can open another bracket, 16.3, there's a point here, I think it was too small, and then plus 1050. So what is going to be the answer? The answer will be 20, actually it is going to be 0.246, yeah? So the omega final will be what? Will be, now am I wrong? I think I've done something wrong here. Because omega final, what is the omega initial? It has to be bigger, yes? So 0.246, yeah, it is bigger in this case. So the answer logically is correct. So in this case, it's going to be 0.246, that is radian per second. Remember, the child is going from the edge closer to the center. That means omega final must be bigger than omega initial. Initial was 0.2. Here, as you can see, it is 0.246. Okay? And that is how it is done. All right, remember I told you there is an easy way where you could do this, yeah? What is the easy way? Instead of doing all this, just remember this for me, okay? So always, whenever they are asking for omega final, just remember this. Omega final will equal to, like directly, equal to moment of inertia, or let's say, yes, moment of inertia of initial of the first object plus moment of inertia, let's say the initial moment of inertia of the second object, multiplied by the initial angular speed divided by the final omega, let's say final moment of inertia of the first object plus the final moment of inertia of the second object. So this is all what you need to know in order to find the omega final angular speed. Then of course, whichever the object you're considering, for example, whichever the moment of inertia, whether it is 1 or 2, you're considering the object that is rotating, will be the same for initial and final. The object that is being rotated will be different. So in this case here, you're going to find I initial for the first one, let's say, and then I final for the, let's say again for the first object, and then let's say you'll find I, let's say final, okay, or initial for the second object first. Let's go by the order so we don't, I don't get you confused here. So I initial for object 1, I initial for object 2, try to find them, and then I final for object 1, not Li. So I final for object 1, you try to find it. I final for object number 2, try to find it. And then all you need to do is plug in these numbers into the equation. Of course, you'll find the omega final. So as simple as this. So you don't have to go through a lot of work. Just remember this step, right? And then find each one of these. Remember, the shape will determine what equation you're going to use. And then you just plug in the numbers and you will find the answer. So in the next questions, you will see that we're not going to go through all this work, yeah? We'll just use the last step and that's it. So remember, the merry-go has 1 moment of inertia because it has a fixed radius, but the student has 2 moments of inertia, 2 moments of inertia because her radius changes. So take a look at this. Similar question to the previous one, okay? We have a bicycle wheel and a reflector. So as you can see here, the reflector is very close to the center, to the axis of rotation, but then the reflector moves away from the axis of rotation. Okay, and I believe, okay, so we're going to do or solve this one here, okay? But I'm afraid we might not have enough time. Perhaps, shall we do this one in another lesson? Let me do it, see if I can do it in 2 minutes, because that's what I've been told. We only have 2 minutes. So let's solve this one, or see if we can solve this in 2 minutes. So let's bring this. All right. Not stamps. All right. So try to write the information that is given. So we have a 2 kilogram bicycle wheel. So the mass of the bicycle, that is 2 kilograms. All right. Remember this. With a radius of, so the radius of the bicycle wheel is 0.30 meter. Turns at a constant angular speed of, so we have initial angular speed, which is 25 radian per second. Next, says when a 0.3 kilogram reflector, so the mass of the reflector, R for reflector, it is 0.3 kilogram. And then at a distance of, so that means the radius of the reflector is 0.19 meter, okay, from the axle. What is the angular speed of the wheel when the reflector slides to a distance of, so this, if this was R1 and R2 is going to be the distance of what? 0.25. Okay, what is going to be the omega final, or final angular speed? So let me write it down here. What is the final angular speed? So remember, we said we're going to do this in one step, yes? So here's what we're going to do. We'll say omega final equals to bracket initial angular, let's go with initial plus initial for the second object, initial angular speed, that is going to be I final for one object, I final for the second object. Yeah, so we can call this one for, let's say, the bicycle, reflector, bicycle again, reflector. Now all you need to do is just find moment of inertia for the bicycle, which is because the radius of the bicycle wheel is not going to change. So initial and final will be the same, but this value, these two values will change. Okay, so let's see. Moment of inertia of the bicycle wheel, it is like a ring, so initial would be the same as final for the bicycle wheel, which is going to be mr squared, yes? So what is m? Okay, let's, so mass of the bicycle wheel is 2 times the radius of the bicycle wheel is 0.3. So 0.3 squared, don't forget. So 2 times 0.3 squared is going to be 0.18, yeah? That is going to be kilogram meter squared. That is one thing. So omega initial and final would be the same. Okay, so I think we still have 1 more minute. What about the initial and final for the reflector? So let's say I initial for the reflector equals to, by the way, reflector is like a point mass, so so once again mr squared. So in this case the mass of the reflector was, what was the mass of the reflector? 0.3. So 0.3 multiplied by the radius, or the initial radius, which was 0.19 squared, yes? So 0.3 multiplied by 0.19 squared, yes? So of course we have 0.0108, yeah? Or you can say, you can have these digits for now. What about final? Omega final of the reflector, because the radius will change, the mass is still the same. So mr squared, yeah? Okay, so in this case, 0.3 multiplied by, what is the second radius? It is 0.25 squared, of course, right? So 0.3 multiplied by 0.25 squared. So of course the answer will be 0.0, that is 188. Of course, we're going to use some roundings here. This is 0. Okay, now all you need is just plug these numbers into the equation. We'll find the answer for this. So, by the way, let's just plug in the numbers here. Omega, or moment of inertia for the bicycle wheel was 0.18. So 0.18 plus, for the reflector, the first one was 0.0108, yeah? Okay, let me keep all the digits for now. So multiplied by what? By So we have, once again, moment of inertia or initial for the bicycle for the reflector, and then multiply by the angular speed. Why are we using the same angular speed? Because they are spinning together. So they have the same angular speed, so multiplied by 25. And then divided by, what was, remember, we said initial and final for the bicycle wheel was the same. So once again, 0.18 plus, what about the final for the reflector? The final for the reflector was 0.0188. Of course, you can round it up, but I would rather to keep them all for now. So all you need to do now is just add this to multiply and then divide by the addition of this two. All right, so let's use a calculator and then get the answer done. So open bracket for this two, 0.18 plus 0.0108, close bracket, multiply by 25, that is the angular speed here, divided by, once again, open bracket for this, 0.18 because it is the same, yes, and then plus 0.0188, and then close bracket, and then the answer here will be 23.9, which by rounding we can say, so omega final will be, by rounding of course, is going to be 24 radian per second. Now, before you see whether your answer is right or wrong, take a look and think for a second. The reflector is moving, let's say, from the center or from somewhere close to the center away from the center. We know that when the mass moves away from the axis of rotation, that means the moment of inertia gets larger, it starts to spin slower, yeah, because the mass will be further from the axis of rotation. So take a look here. In this case, because the mass went far, so omega final must be smaller than omega initial. So let's compare the two. Omega initial was 25, omega final is 24, so logically it makes sense, and of course the answer is correct. So that is it for this session. Keep practicing. I'll see you next time, inshallah. Assalamu alaikum.